Welcome everyone. I am Lorenzo Ferretti from Università della Svizzera italiana, and I'm going to present a work we did in collaboration with the Columbia University. And the work is about leveraging prior knowledge for effective design space exploration in high-level synthesis. So for application with high performance requirement, an hardware implementation of the desired functionality may be required. In this case, designers may use high-level synthesis tools to generate the corresponding hardware implementation. The designers usually start from a software description that may be a C or a C++1, and this is given in input to the HLS tool that generates the corresponding RTL implementation, which is characterized by certain area and latency values. In addition to these, high-level synthesis tool can be guided with the use of HLS directives. HLS directives target a specific region of the code, and they have an impact on the resulting hardware implementation. So in this case, loop unrolling, by specifying a different loop unrolling factor, allows the generation of circuit variants with different area and latency values. HLS directives can be combined together with other ones. So in this case, we are seeing the effect of loop unrolling and function inlining. And in this case, we have to consider all the combination of the possible loop unrolling factor and the effect of the function inlining directives. And this leads to a problem. And the problem is that the design space grows exponentially with the number of directives and directives values that we have. However, from the design space exploration point of view, only few of the resulting implementation are interesting. In fact, designers are interested only in the Pareto optimal implementations that are in the configuration space. This leads us to the HLS-driven design space exploration problem, where the goal of the problem is to retrieve a close approximation of the real Pareto frontier while minimizing the number of syntheses required by the process. Because the synthesis process is an extremely time-consuming process that may require even days of synthesis for a single implementation. So in this example, we have a design space with more than 1,700 configurations. And ideally, goal of a good exploration is to synthesize only few implementation, which results into an approximation of the real Pareto frontier. So this is the design space exploration problem, and let's see how this has been addressed in the state of the art by other researchers. So in literature, we can find two main approaches. There are model-based methodologies in which designers build a model according to their knowledge of the HLS tool and of the effect of the HLS directives. So in this case, the model gives the designer gives an input to the model the specifications and the set of HLS directives, and the model pre-estimates the resulting area and latency implementation for the given input. Those models, those approaches are usually extremely accurate. However, they are limited in the number of directives that they can consider, and they are also strictly related to specific HLS tools. On the other side, there are black box-based methodologies. And in this case, instead of creating a model with the designer knowledge, the model is created inferring some knowledge from a training set. So the designers gives in input a set of HLS specifications and HLS directives, and the models learns automatically how the HLS tool behaves. Now, similar stance always belonging to the black box-based methodologies, there are refinement-based methodologies. These methodologies may rely or not on an initial training phase, but they are characterized by the fact that for each new implementation generated, the model is updated with the new gained knowledge. And those black box-based methodology with respect to model-based methodology, they require usually a higher number of syntheses, but they are agnostic both to the high-level synthesis tool considered and to the number of directives. The work we are presenting here belongs to the black box-based methodology category. The idea we are proposing is to leverage prior knowledge from a set of already performed design space exploration. So when we have in the standard approach, when we have to perform a design space exploration, the designer defines a configuration space, which is the set of all the configurations that we want to consider during the design space exploration. Only after the design space exploration process, the corresponding set of Pareto optimal implementation is identified. And what we would like to do is to use the knowledge gained in the past across many different design space exploration to guide the exploration process for a new target application. So this leads to a few problems that we have to solve. First of all, we have to find a way to identify similarity among different applications. So given a new target application, we have to find a good candidate one from which we want to leverage the prior knowledge. Then once we have identified this source, we have to find a way to map the configuration from the source design space into the target one. And once we have been able to map the configurations from the source space to the target one, we have to verify that the set of Pareto optimal implementation that we have retrieved is close to the real one. Now let's see how our methodology implements this idea. So we have a pipeline, and this pipeline, there are three main processes. There are signature encoding, similarity evaluation, and the inference process. So we start for a set of design and configuration space, which are given in input to the signature encoding process that generates a target signature, which is a unique representation of the design specifications and of the configuration space. This is given in input to a similarity evaluation process that looks into a database of design space explorations and returns the most similar source that we have available in our knowledge base. This source is given an input to the inference process that looks again into the database and retrieves the Pareto optimal configuration from the source application. Those configurations are then mapped into valid configuration from the target application, and those are given in input to the HLS tools, which synthesize them and retrieves the corresponding area and latency values. Now let's look at the different steps of our methodology one by one. So let's start from the signature encoding. A signature encoding is a compact representation that abstracts both the specifications, so the code, and the configuration space. The specification encoding is a simplified representation from the HLS point of view of design specification, while the configuration space descriptor describes in a compact way all the possible configurations that we want to explore in the design space exploration process. So let's look more in detail at the specification encoding. This is a simplified representation in the form of a string of the input application, the specification of our input application. So this highlights all the structure that can be targeted by HLS directives. So element of interest in our case are functions, the parameter passed to a function either by value or as a pointer, the array allocation, struct allocation, the presence of loop, read and write operations, function call, and the hierarchy among all those operations. So let's look at an example. This is the last step scan from the radix sort benchmark in the Mac Suite benchmark suite. And in this case, we have a function which takes in input two arrays, and then there are two nested loops, and inside of the two loops, we have two reads and one write operation. So this code is given an input to a compiler pass, an LLVM pass that we have generated, that creates the corresponding specification encoding representation, which is a really short signature for our application. Now, let's keep in mind this example because we will use this example over all the other phase of our methodology. So let's look now at the configuration space descriptor. As I mentioned before, this describes all the possible configuration that will be explored in the design space exploration process. So in our configuration space descriptor, we have created a simple domain-specific language that describes for each portion of the code, so in this case, for example, for the array bucket, that we want to use a specific resource type, and we want to apply the array partition directive. In fact, our configuration space descriptor for each line defines a directive type, a location for the directive that we want to apply, and a set of directive values. The tuple of those three elements is a knob, and the knob is an important element in our exploration, in our methodology, because it will be used in order to evaluate the similarity across different applications. Let's look now at the similarity evaluation then. So in order to evaluate the similarity among different applications, we have defined a similarity metric. This is a linear combination of specification encoding and configuration space descriptor. Well, for the specification encoding, since we have two strings, we look at the longest common subsequence among a target and a source application. While for the configuration space descriptor similarity, we have defined a custom-made similarity, which essentially looks at the similarity among source and target knob. In order to define this similarity, we have to find a mapping function that maps the source knobs to the target ones. And for both of the similarity, the values are normalized such that we have a similarity score which is included between 0 and 1, which 1 means a high similarity among target and source application. So let's look at the configuration space similarity. I say that we need a mapping function. As a mapping function, we have used the top-down mapping, which maps the knob from the source to the target. And it maps the first knobs of the source to the first available knob in the target. So here we can see how different knobs are mapped from a source to a target. Let's now look at an example of similarity evaluation among different knobs. So here we have a mapping among target and source knobs. And let's look at the similarity evaluation for knob 6 from the target and knob 5 from the source. Both are unrolling type directives. And when we evaluate the similarity among those elements, we evaluate the similarity as the distance among the closest elements that we have in the set of values for the target knob and the one in the set of values for the source knob. So in this case, since we have almost the same elements, we are considering the distance between 1 and 1, 2 and 2, 4 and 4, and then we go on like that till we reach 128, which is not available in the source. That means that we will have a distance which is higher than 1, since we have to map 128 to 64. Now, let's look at the differences among the similarity. Here we are looking at a chart that shows the similarity, both the specification encoding similarity and the configuration space descriptor similarity for 39 different functions from the MaxSuite benchmark suite. So on the y-axis, we have the sources, and on the x-axis, we have the target functions. And here we can see that while we measure the similarity among when we measure the similarity among different applications, they may have a high similarity in terms of specification encoding, but low similarity in terms of configuration space descriptor. In this case, a darker color means higher similarity, while let's say lighter color means low similarity. And that's why it's important to combine them into a unique similarity metric, which is the linear combination of the two. So by looking at this matrix, when we want to decide from which function we want to infer the leverage, the prior knowledge, we select our target application. Let's see the first one. We look for the most similar source, and then we pick the most similar one. In this case, keep in mind that the elements on the diagonal is a similarity with respect to themselves, so we will never select these as a valid source. Now, let's look at the inference process. So once we have identified the proper source and we have retrieved the set of Pareto optimal configuration for that source, we have to map them into a target space. And how we can do that? Well, we do that in a similar way as we calculate the distance among the different knob values. That means that we map the closest configuration, the closest element of the source configuration into a valid element in the associated directive set for the target knob. And let's see an example in this case. So here we have different source, a source with different knobs, and the target knobs. In this case, we have that the first and the second knob from the target are not mapped because there were no available knobs of the same type in our source design space. That means that the two knobs are unmapped, and our methodology in this case select randomly a valid value for those two knobs. While for the other elements for which we have knobs, what it happens is that we map the knob values to the closest available elements in the set of directive values for that knob. So for example, for K1, which is array partitioning directive, we map cyclic to cyclic and 256 to 256. The same for K4 and K5 of the target, while for K6, we should map 64 from the source to the closest one in the target. And since the highest value available in the directive set values for that knob is 16, this is mapped to 16. We also introduce a notion of rank among the Pareto frontier. And we introduce this notion because we want to explore the neighborhood of Pareto optimal configuration. So let's see how we define these rank Pareto front. So when we look at the design space and then we want to find the Pareto optimal configuration, this is what we call the first rank Pareto frontier. But then what we do is to peel the design space from the Pareto elements and to calculate again the Pareto front. The resulting Pareto elements are the second rank Pareto front. And then we can iteratively peel the design space in order to retrieve up to the ith rank Pareto front. Let's see at the results obtained by our methodology. Well, we have evaluated the quality of our methodology considering 39 different functions from 50 available in the Max Suite benchmark suite. And for each of those, we've performed an exhaustive exploration, and we have used the result of the exhaustive exploration as a ground truth to evaluate the quality of the design space exploration. And we have measured the results in terms of average distance from a reference set, which is a metric that calculates the distance among a Pareto frontier, that is the ground truth, and the one retrieved by our application. Now, let's see at the effectiveness of our methodology. Here we are looking at the inference process for the last step scan function that we have seen before, while we infer the knowledge from the most similar application according to our similarity rank. In this case, we have both a high specification encoding similarity and a configuration space descriptor similarity. And we can see that we are able to obtain a close approximation of the real Pareto frontier. And in fact, we obtain a really low ADRS values. The ADRS value of 0 means that we have obtained a perfect approximation of the Pareto frontier. But let's see what happens when one of the two similarity results in a poor similarity. So here we are looking at what happens when we have a low specification encoding similarity. So in this case, what it happened is that we are not able to map properly the knob from the source to the target. And the result is that for the map that are mapped properly, we are able to approximate well the Pareto frontier, while for the knobs that are not mapped properly, we cannot infer any knowledge, and that results in a portion of the design space which is not explored. What happens when we instead have a low configuration space descriptor similarity? Well, in that case, even if we have a good mapping, let's say, what it happens is that we are not able to infer the proper directive values for the mapped knob. And in this case, we can see that we are getting, let's say, the shape of the Pareto frontier, but the knob values are off from the real one, so we are poorly exploring this region of the design space. When we have both low specification encoding similarity and configuration space descriptor similarity, instead the results of the exploration is really poor, and in this case, only a single Pareto point is retrieved. So let's see now at the effectiveness of our similarity metric. Here we are evaluating the quality of the selection of the proper source made by our methodology. So in this case, we are looking at the aggregated ADRS. That means that we have collected all the results from the inference among all the tested applications. And we are seeing the results obtained when we perform the inference from the first ranked source, second, third, and so on. And we can see that the selection of the best source, according to our metric, is the one that leads to the best results in terms of design space exploration. So let's now see at the results in terms of effectiveness while we evaluate our selection criteria. So in this case, we are evaluating our methodology, prior knowledge, with respect to other three selection criteria. The first one is Oracle, which is a perfect choice made a posteriori of the best possible source for the exploration. And the other two are an average and a random one. The average is what we obtain through the average of the results obtained by selecting all the possible sources as a good candidate, while the random is what we obtain if we select randomly points from the design space. And we can see that the results of a prior knowledge approach performs 1 order of magnitude better than the average and 2 order of magnitude better than the random. Here we are instead evaluating the effect of selecting multiple Pareto frontier rank for the inference process. That means that we are inferring not only the Pareto optimal one, but we are considering the neighborhood of the Pareto optimal ones by selecting multiple Pareto frontiers. And we can see that while the IDRS decrease non-linearly, while we increase the number of Pareto frontiers, the number of syntheses grows up linearly. Now let's see at the results of our methodology with respect to state-of-the-art one. So here we have compared our methodology with respect to other 4. 3 of them belongs to the refinement-based category, and 1 belongs to the model-based category. Here we are looking at the results for different sizes of the configuration space, and we are measuring the number of syntheses required to reach an ADRS goal of 0.04. And we can see that our methodology is able to perform better both with respect to refinement-based approaches and also to model-based one. And this is a really good result since we are able to obtain better results without having the drawback of model-based methodology. In fact, our approach is both agnostic to the high-level synthesis tool considered and also to the number of directives. This is what we have done till now. And our future plan is to improve our methodology by introducing a unique representation both for the specification encoding and for the configuration space descriptor, such that we can have a better representation of the problem and also a better similarity metric for identifying the proper source. And more importantly, we're planning to release the database of design space exploration soon, such that you can use it to test it for your design space exploration methodology or as a source of knowledge for future design space exploration strategy. Thanks for your attention. If you have any question, I'm available to answer you.